Welcome to this session in the course Data Structures and Algorithms. Last time we looked at the algorithm for converting an infix expression into a postfix expression. Today we shall see a C++ program implementing that logic. Here is the algorithm that we shall use. Given an infix expression as a string input, we need to create an output string which is the postfix expression. So, the process is very simple, which was explained last time. Validate the infix expression first. If the fixed expression itself is not valid, then I will display an appropriate error message, otherwise I proceed with the conversion. The conversion process itself again is very simple. Firstly, I traverse the infix expression character by character. So, I will have an outer iteration which will look at every incoming character of the infix expression. Now, if the character is operand, then append it to the string postfix. If the character is not operand, it will be an operator. If it is an operator, we will do the following. Firstly, if the operator is opening parenthesis, push it to the operator stack and continue with the point traversing further. If the stack is empty and operator is not closing parenthesis, then I push the operator on the stack. If his stack is not empty, then I will compare the current operator with the one which is already on the top of the stack. Remember, last time we discussed this, that we need to worry about the precedence of the two consecutive operators that might come. If the operator that we now encounter has a higher precedence, push the operator on the stack. If it is a lower precedence, then we have to append the top element of the stack to the postfix string, pop the top operator from the stack. Now we will continue doing these operations 1 and 2 till a opening parenthesis is encountered or the stack becomes empty. Finally, we will push the current operator, but not the closing parenthesis on the stack. At the end, I will append the remaining operators from the stack to the string postfix by using top followed by pop till stack becomes empty. Simple procedure. Let us look at its implementation using a C++ program. First, we identify the member functions which we need to write in order to achieve this conversion. Check parenthesis. This is a function which we will write. The parameter is an infix expression which is a character array. It will be called from the validate function and it will return true or false. Purpose is to check if the open and close parenthesis match properly. Is valid is another function. The parameter is the current character. Now, the current character is valid only if it is either an operator or an operand. Note that for this example, we have presumed that all our operands are single letter operands A, B, C up to Z or capital A, B, C up to Z. This is of course a simplification, but for the current purposes this is sufficient to check whether the character is valid or not using this. Validate is another function which validates the entire infix expression which is a character array. It will return true or false to the main function, and the purpose is to check whether the entire expression is valid or not. Of course, while executing the logic of this validate function, it will invoke other functions like is valid and so on. Is operand is again look at the current character and it will check whether the current character is an operand, that is small a to z or capital A to z. Priority number is actually an artificial number which we are creating to be allocated to every operator that we encounter. So, the parameter to this particular function is a character which is an operator and it will determine the priority of the operator. The artificial numbers that we have decided are 0 for the highest priority operator, namely raised to, followed by 1 which will be used for multiplication or division, followed by 2 which will be used for addition or subtraction and so on. Check priority. This will compare the current operator and the top operator on the stack, and it will return true or false depending upon which has the higher priority. Infix to postfix, this is a function which takes infix expression and postfix expression as strings, which are character arrays, and it will return the postfix string to the main function. Input of course will be the infix expression. So this is the main activity, converting a valid infix expression into a postfix expression. Let us look at the program itself. What we have done is, looking at the program, we will also look simultaneously at the logic which the program is trying to implement. First, traversing the entire infix expression. So for counting the number of opening parentheses and closing parentheses and finding out whether they are matching or not. So this is the check parenthesis thing. It declares some temporary variables, and while there is a valid character in the input string, namely infix ith element is not \0, which is the end of the string, I will examine if this is equal to opening parenthesis. If it is, I add 1 to the count of open. If it is closing parenthesis, I add 1 to the closing parenthesis count. If close is greater than open, then I will have to say this is not valid. I will return false. Otherwise, I will increment I by 1 and go back, continuing with this iteration. If open is exactly equal to close, which is what is required for a valid expression, this function will return true, otherwise it will return false. Simple program, simple function. This is the one which will check initially whether the parentheses match in numbers. Next is valid function. The purpose of this function is to check whether the character that comes in the infix expression is either of a to z or small a to z, which corresponds to our operand, or opening parenthesis, closing parenthesis, star, plus, minus, slash, or raised to, which are the valid operators. In short, is valid will check every character in the expression and will confirm that it is either a valid operator or it is a valid operand. Once again, please note that we are presuming that our operands are variables with single character name a to z, a to z. We continue looking at the next function. This is the validate function. Its input is entire infix string. We need to traverse the string, and if the character is not an operand or operator, we should return false, else point to the next character. So while this string is not ended, we will call the is valid character for that particular ith element of the infix string, which means the ith character of the string. If it is not valid, as shown here, it will return false, else it will go to the next character. This way it will check everything. It will finally check parenthesis given the infix string. If that is false, then again it will return false. If the parentheses match and if all other characters are valid, this function will return true. Again, a very simple exercise, a simple function which will validate our expression. Next, let us look at assignment of priority numbers. These are numbers which I mentioned to be indicating the priority of various operators. This will return values 0, 1, 2 or 3 depending upon the operator. So see the simple implementation. We look at every char, which is an operator, which is the character in the string which is identified as the operator. If operator is this, it will return 0. If operator is star or operator is slash, it will return 1. If it is plus or minus, it will return 2, and if the operator is a opening parenthesis, then it will return 3. This is the end of the function. We also need to check the priority when we are actually implementing the infix to postfix conversion. This will require looking at the current operator and looking at the operator which is already on top of the stack. So it has two parameters. All that it does is it calculates the priority number for the current operator, calculate the priority number for the top operator. If the current operator has a lower priority value than top operator, which means it is of a higher precedence, then it will return true, otherwise it will return false. So please remember, check priority will return true if the priority of the current operator is higher than the priority of the operator on the stack. One more function that we need is to check whether a particular character is an operand. The current character is given. We already know that we have assumed that the operands will be variables, single character variable names, capital A to Z or small a to Z. All that this small function does is checks whether the characters are within this range. If it is, then they are truly these characters, otherwise not. So notice a simple return statement is used, and if these things are true, the function will return true. If any other character comes here, this will return false. A simple implementation. Now we come to that part of the program function which actually does infix to postfix convert. This has two parameters, infix as the input array and the postfix array, which is actually assembled in an array called answer in this function. So I declare these current char I, j, etc., etc. I declare a char postfix internal array which I initialize to blank. I have a stack char which is the operator stack, and now I start my procedure, which is I look at the infix string character by character, and as long as the character is not \0, that means as long as there is a character in the infix string, I will examine that character and act accordingly. So this is what we mean by traversing the infix expression. We put the ith character into the current char, and this current char will now have to be handled. There are 2 or 3 segments which will handle this current char. We have identified them arbitrarily as 2.1, 2.2, the 2 segments of the code which will follow one after another. After this, I is incremented and next character is examined. When the entire traversal is complete, there is another segment which will possibly help us assemble the final output. Finally, since we have assembled the final output in postfix string, we will copy that string to the answer, which is the parameter to be returned. That is the end of the function. Let us look at what is the code for 2.1, 2.2 and the code for 3 in the subsequent slides. These incidentally are point numbers which are given in our algorithm, so you can easily identify what is the logic that we need to implement here, what is the logic that we need to implement here, and what is the logic that we need to implement here. So the code for 2.1, that is a character is an operand, we need to append it to the string postfix. Very simple, is operand, then postfix j is equal to current character j plus plus. Notice that postfix string will get assembled one by one as and when something is to be appended, and that is why the variable j will increment independent of other variables only when something is appended to the postfix string. Let us look at 2.2. If that is not so, then we have to do the following, namely that it is an operator. If it is an operator, then if the operator is opening parenthesis, push it to the operator stack and continue with 0.2. Okay. So the code is else it is an operator, that is it. Now if it is an operator, we have to do variety of things. This 2.2.1 is if the current char is opening parenthesis, then operator stack dot push current char means it will push it onto the stack and increment I. Continue means go to the next iteration corresponding to I. So this is again a simple functionality. Let us look at what happens if stack is empty and operator is not closing parenthesis. This is the point 2.2.2 in our algorithm. In such a case, we need to push the operator on the stack. So else it is an operator, and we have done this. Now we are coming to code for 2.2.2, which is very simple. If operator stack empty and current char is not equal to closing parenthesis, operator stack push current char. Simple implementation. Let us look at 2.2.3 next. For your benefit, we have repeated the logic of 2.2.3 in words which was already included in the earlier explanation. Let us very quickly go through it. If stack is not empty, then I have to compare the current operator with the one which is present on top of the stack. If it has a higher precedence, push the operator on the stack. If it has less precedence, then append the top element of the stack to the postfix string, pop the top operator out, continue these till you encounter opening parenthesis, and finally push the current operator but not the closing parenthesis on the stack. So this is the logic implementation. This is the code for 2.2.3. It is slightly larger code, but you will be able to easily understand it. First I check priority. If when I check priority, I will do operator stack dot push. If the priority is not appropriate, then I will have to look at removing the top item from the stack and pushing it onto the output string, provided there is a top operator. So this is the entire logic of 2.2.3b, which says while the operator stack is not empty, if the operator stack top is opening parenthesis, then I pop it off and break. If what now I have to do is, I have the postfix string, I will have to append to that postfix string the top of the operator stack. So I take the operator stack dot top and assign it to the jth element of postfix string and increment j plus plus. So this is the equivalent of appending. Finally, I pop off the top of the stack which has already been accounted for by including it in the postfix string. This is the end of while. At the end of this while, if the current character is not equal to closing parenthesis, then I have to push the current character, which is an operator, onto the stack. This is the end of this else statement. It may appear slightly complex, but when you read the entire program in one go, which is available at the end of the slides here, you will be able to understand it very clearly. Next, let us look at appending the remaining operators from the stack on the string, which is very simple. While operator stack is not empty, all that I do is I look at the top of the operator stack, and that element I assign to the jth element of postfix, which is the next in the postfix string, and pop that off. Of course, I increment j plus plus. I do it for all the remaining operators on the stack. This completes my program, and now I can write my main program, which is rather simple. I have an infix string, a postfix string. I collect from the user an infix string. I validate the infix string. If the validation returns false, then I will give a message, sorry boss, you have not given me a correct expression, so I can't do anything, and return -1. Otherwise, I will output the infix expression indicating that it is a correct expression, simply invoke infix to postfix, which is the main function that I have written, supplying it as a parameter infix and collecting back the parameter of postfix, and I simply print the postfix string. Notice once again that the programming is actually easy, primarily because although we have to write a lot of functions, primarily the STL has provided all the operations related to stack which we did not have to rewrite. Once again, you are reminded to look at these references which were indicated even in the last time. To conclude, we have considered the infix to postfix conversion process in a previous lecture, and in this session we looked at a C++ program which implements such a conversion. In the subsequent sessions, we will look at the evaluation of a postfix expression. Thank you.